Hi guys, welcome to today's Sunday contest. Today we'll be discussing problem number 3, and problem number 4 was, I think, easier than problem 3. I think so. We should discuss problem 3 first. So yeah, let's get started. Okay. Yeah. So the problem. Okay, I'll just explain the problem first. So basically, you are given a graph. Okay. Check my recording. Yeah. So we are given a graph which is directed plus weighted. Okay. And now let's say your graph looks like this. Okay. And okay. And then all the nodes are zero indexed, and all the nodes also have some labels. So let's say this node has label A, this node has label A, this is C, this is B. Okay. And also your weights, let's say 1 2 5 7 positive weights. So what you need to find out is you're traveling from 0 to n minus 1. In this case it's 3. There are n nodes up till 50,000, which is I think 50k nodes. So you want to travel from 0 to n minus 1 such that there are no more than k consecutive identical characters. So in this example, let's say k was given as 1. So you cannot go through this path. This path is AACB. So here A occurs twice consecutively, but it's violating this condition. So you cannot do that. What we can do instead is we can travel to this path, which is ACB. From 0 you went to 2 and then you went to 3. Okay, so in that case the weight that you got was 12. So now what you have to return is, among all the possible paths, you have to return the minimum edge weight, which doesn't violate this condition basically. Okay, so in problems like this, obviously the graph is weighted and you've got some constraint. So the first thing that you should be doing is scrolling down to see the constraints. So here k is 50. K means how many consecutive identical characters you are allowed to have in your path. So k can go up to 50. So this kind of constrained weighted graph problems generally fall into Dijkstra with DP. Okay, because Dijkstra itself is a dynamic programming construct, and if you add more constraints, it still remains a dynamic programming construct with just more constraints. So needless to say, it's a Dijkstra plus DP problem, and the trick here is to model the graph correctly, and then it's a standard Dijkstra. Okay, so how do we model this graph? So let's say you are standing at node U, and you are gonna visit. You can visit all the nodes V1, V2, V3, and so on. Okay. Let's say this guy had character A, this has B, this has C, and we can have any characters. And you're standing here. This is you, and let's say you came from somewhere. I mean, doesn't matter where you came from. Sorry. Let's say this is A, B. The okay. The nodes are the labels, not the edges. My bad. And then you got all of this. And you came from somewhere. Doesn't matter where you came from. And let's say the label here was A. Node U had A. So what do you see here? What information do we need to encompass this state? first is the ID of the node, right? Second is the A, like what character it has. So character it has, which is A, right? Or this can also be called as last character, right? Because that's the last, you are standing here, you have traveled all the graph, and at the end you are standing at U. So that's the last character that you're seeing as of now. And what else do we need? We need how many times did you see that last character, right? So frequency. So what I mean by how many times is, like, so let's say you have seen A once here, for example. Okay. So obviously you might have come to this state from somewhere, right? From somewhere you came to this state, and the number of times you saw A, like you came through some path, let's say the path was A, B, C, A, C, C, A, B, A, and A. Okay. So then you're standing here. Let's say you came through this path, for example. So you can define the frequency as the number of times that you saw the last character consecutively. Okay. Yeah, that's your F. So in this case, F is let's say 2, because you're seeing it twice. So we also have to define F. Just give me one moment, guys. Yes, so we also have to define F. So F is part of the state. So in this case, F is 2, because this is the path you have. Sorry. Okay. And now you're trying to go to V1, which is A again. So from F, you're trying to go to F plus 1, because both these last characters match. Both of these are A's. And this is V1. So in this case, you're trying to go to F equals to 3. Okay. So your graph will have these 3 states. I mean, each node will have these 3 states. So what we can do is we can define a dp of ijk. Pad convention, dp of u last, which is last char, and the number of times we saw that last char occur consecutively at the end, right? So in this case, if last char was A, and the path you followed to reach this A had, let's say, some character like this X, so it had 4 consecutive A's. So in this case, your graph state would be U, last char is A, and then 4. Okay. So yeah, having this information is useful, and it correctly describes the entire state of all the nodes that your node can be in. Okay. And X is basically the breaker. So let's say X was just X, so it doesn't matter. So the reason why we are writing this DP is because we are only interested in how many consecutive number of times the last character is occurring. Because if you do that, then you're also ensuring that in the remainder of the string you are following the correct DP and you're not violating any constraint. That's why. Okay. So dp of u last square and f is equal to um, okay, so we want to go to v, right, node number v. So some view you're trying to go to v. This is the last square of, let's say, L1, this is last square of L2, and this is weight W. So how do you write this straight? So dp of V, L2 and frequency F. So let's say L1 is equal to L2. Okay, so let's say both are L1 and L1. So in this case, what will happen is last square will remain the same, L1, and the number of times it occur was f plus 1. Let's say the frequency is f, because f plus 1, because both are same. This would be equal to dp of u last square L1 f plus w. And obviously you'll put a minimum condition. In the Dijkstra we do this, right? If dp of v L1 f plus 1 is, if it is greater than this, only then do this, only then execute this. Okay. And you also have to take care of the condition where f plus 1 is, only do this if f plus 1 is less than equal to k. So you just put and here, f plus 1 less than equal to k, because we don't want our suffix to violate the condition. And let's say L1 is not equal to L2. Okay, in that case what we'll do, it's very simple. We just do dp of v L2 and 1, because up till here we were seeing, let's say, a's, and now we are seeing a b at v. This is u, this is v. So obviously our last character is b when you're standing at v, right? So it's just you're seeing it once basically. So this is equal to dp of u L1 f plus w, obviously with the condition that let me just select that, obviously with the condition that this guy is greater than this guy. Only if this is happening, only then do this. Okay, so yeah, this is the transitions, these are the transitions, and yeah, I'll just show you the code to make it more intuitive. So I'll first discuss this DP solution, and then we also have to optimize it, because seems like it when I submitted this DP was giving me a memory limit exceeded, so I had to optimize. I'll discuss the optimization now. Okay, later I mean. So okay, what I did was wait a minute, sorry. Yep. Yeah. So you have this node, I defined a node which is distance, ID, how many times it occurred, and the last character. Okay. So this correctly encompasses the node state. Then what I did was created a graph, wrote the DP is a 3D DP, so n k plus 1 and 26, which is k plus 1 is basically the at most state that we saw, 26 is the character. So basically last char can be till 26, frequency can be till k, this can be till n, so it's nk into 26 of memory. Everything is in packs, and then I took a priority queue, wrote a custom comparator on the distance of the node. Okay, so you get the lowest distance to show up at the top. Push the 0th node, because now the 0th node has at most one character, right? Because we are standing out that node and we are seeing these labels of 0 minus a value. So you have to initialize it like this. So let's say this is 0th node, and let's say it had a g. So dp of 0 and then 1g is 0. Okay, because 1 is the k, it contributes to the answer, right? So if you go to first node and you see a g again, then there are 2 g's and not 0 g's. So yeah, this should be 1, because you're seeing at most you're trying to calculate for at most one character, last character, which is g. So this is 0. Initialize the distance with 0 because we are starting from node 0. So distance will obviously will be 0, and we want to reach till n minus 1 node. Yeah, I did that, and then just the standard Dijkstra. So if the distance is not equal to what we saw earlier, just continue. This is again I think it's kind of a modification of Dijkstra. It's called SPFA, shortest path faster algorithm, but people confuse it with Dijkstra, so I just want to clarify that it's not Dijkstra, because if it was Dijkstra, then I wouldn't be needing this condition at all. But since we are having all the states and stuff, it's paramount to have this condition so that we are not processing the same state multiple times. And then just take the next edge, which is v. You're trying to go from u to v, and this is the condition that we discussed in our drawing. Basically this entire thing. So if your last character and your current character are equal, and check this, if it's less than k, you push it, else they're not equal, then dp of v1 that we discussed. All these conditions are what we discussed, right? And at the end, what you're doing is you're trying to go till n minus 1, and your last character, which is j, could have occurred any number of times up till k, identically, I mean consecutively. So you just iterate on all of those dimensions, get the answer, and return it. So now the problem here is that this code was giving me an MLE, like you saw, 994 out of 999 cases passed. So the reason for that is our DP is very huge. It's like 50k times 50 times 26. So I calculated this, it was greater than 256 MB in the worst case, and this is not acceptable. So what we can do is, instead of DP, we don't need to store all these states, because we will not be obviously touching all the states. We'll be only touching the states that we actually require, that the algorithm actually traverses. So how do you do that? So instead of DP, what you can do is you can have a map which will just say state and distance. Okay, so state is still a three-dimensional thing, right, that we defined here. This is your state. State is there are 3 dimensions to a state. There is a node u, there is a character, there's an alphabet alpha, and there is an integer up till 50, which is the frequency. So can we encode this state? Yes, we can. We can run some encoding on this state such that let's say u occupies the first 16 bits, alpha is occupying the next 8 bits, f is just at the end. So basically what I'm trying to do is I'm trying to encode this state into a single integer, to a single long if you must, so that I can take a map of long and distance. Okay, so as soon as I feed the state inside it, I get the distance out of it. Same thing the DP was doing, but it insisted on taking these 3 states always. Okay, so if I run some encoding on this state, then I will be able to compress this using the map. So that's the idea. You have to write an encode function on the state and plus use a map. So this is your memory optimization trick. I'll just show you the code quickly. Yeah. So it's the same node. This time it's in a struct, doesn't matter. And just ran the encoding. You can learn more about encoding by googling how to encode 3 integers, or how to encode multiple variables into a single and get a single variable out of it. It's pretty easy. Generally, the way to do it is just by shifting the bits and getting a unique integer out of it. That's the idea. And I just took a map now, and everything else is the same. So whenever you want to, let's say, get the distance, then you first encode your current state, and then do a lookup on the map. So that's the core idea. Everything else is the same basically. Okay, cool. Um, okay, thank you guys for watching. I'll be seeing you in the next one. Bye.